Hello guys, this is Sir Mike and welcome to the past paper recording of the IAS Unit 1 motion graphs. Today, in today's lesson, we will be doing past papers regarding graphs. We will be discussing whatever we have studied in the previous lectures and we will be implementing that in the situations that comes in the questions. So I have compiled all the questions for the last 7-8 years so that we can discuss them one by one. Might not be possible to do it in one video, so we'll be doing another lecture after this. So there'll be a couple of them. First of all, starting off with a question of 2017, that is a 2017 material. Yep. No, this is not the material 2017, this is rather syllabus after which the 2017 syllabus. So yes, this exam paper I've got no idea what year it is, but for the first question I've got an idea. It's in specimen paper, I think. Okay. A ball is thrown upwards with the velocity v1. So, relax. There's a ball that's going upwards and it has got a velocity v1. The velocity time graph for this initial part of the motion is shown. The time of contact with the ground can be taken as negligible. So time of contact is negligible. That's what they have given. See, it's negligible. There's like it would have been like this if there would have been any time while the ball was in contact with the ground. Okay, initial part of the motion that okay. Assume that the resistive forces are negligible. Describe the motion of the ball from time 0 to time 3. Now, if you actually have understood my previous lesson, you would have like seriously, you should have an idea. If the ball would be thrown vertically upward, the velocity of the ball is going to reduce. Eventually, at maximum height, it would reach 0. Then the ball will tend to come down and it might go even past the point where it was thrown from. Eventually, it would bounce, and as it bounces, the direction of the velocity is again going to change. So this question has both of the scenarios that we have discussed individually involved in it. Stay very focused. First of all, I'm just going to put values so that you can actually understand. For example, if I throw the ball from 40 meters per second, at the maximum height, this ball would reach zero velocity because at maximum height, the velocity would become zero. Then when the ball starts to come down, the direction of motion is going to change. That means the velocity starts to increase, but in negative. Because like if it was going up, it was positive. So hence it is coming down, it would be negative. So the values of velocity are increasing, reaching a certain particular value. That's v2. That is the velocity before hitting the ground. At v2, it actually hit the ground, and when it hits the ground, just because the time of contact is 0, it starts to move up again. So the direction of velocity again changes and become positive, and now since it's going up, it would be decelerating. At time 3, it would again come to rest. That is the maximum point. So how can we start the answer? Describe the motion of the graph between time 0 and time t3. I would be answering it accordingly. Ball is thrown upwards at velocity v1. It goes under uniform deceleration, and at time t1 it reaches maximum height. So at time t1 it reaches maximum height and velocity became 0. Now at time t1 ball starts to come down. At time T1 ball starts to move down, velocity increase, velocity is increasing in negative as direction of motion is changed. At V2, velocity V2, ball hit the ground, hits the ground. So that's pretty much it. And then bounces back, bounces back with velocity V3, and at time T3, it again reaches maximum height and came to rest. Let me just draw the whole motion for you. There's a ball that is thrown upwards. The ball goes up. Now, this is the ground. Understand my point. I'm standing over here. I threw the ball up from this point. Ball goes up, reaches maximum height, v is equals to 0. This is reached at time is equals to t1, and the ball was thrown with v1. So ball was thrown up with v1, reaches maximum height, became 0. If it's thrown at this point, it reaches maximum height, becomes 0. Start to increase the velocity, and then passes that point, goes to the ground, hit this point, it has got maximum speed, that would be equal to v3. V3 or V2? V2. That would be equal to V2. And then it bounced back again with V3. And again at time T3, it comes to rest at the maximum height. And this V2 would be at time T2. So this is the whole motion of the graph that I summarized and described in front of you. This is very simple. If you actually understand the concept, if you do not understand the concept, this is gonna be a serious pain in the ass. You can't imagine. Okay, so moving on. If you realize, all the time the velocity time graph has a same gradient. Now, the acceleration is gonna be the same. The deceleration is same because throughout the gradient of the graph is not changing. In the next step, they would ask you something like this. Yes, draw an acceleration time graph on the axis below for the motion of the ball from time 0 to t3. You can ignore any temporary change in acceleration on impact with the ground. So you are going to be like, you ignore the temporary changes. That means throughout the journey, the acceleration is going to remain the same. So if throughout the journey, the acceleration is going to remain the same, that particular means that acceleration is going to be same and the value is going to be 9.81. So acceleration is going to be negative 9.81 because I have taken the upward velocity as positive. If the ball was thrown up and velocity was positively decreasing, that means upward velocity is positive. And whenever upward velocity is positive, the acceleration is supposed to be negative, and the graph would be somewhere like the over here, 10, 5, 10, something like this. And then you can plot it around like this, 5 and 10, and then you can write 9.81 and negative. So graph, you can make a straight line, even though if you don't like why I'm making it away, like just make it away. They're just asking about the sketch or draw. They're asking about draw. And yeah, I need to draw that. So I'll be doing it as 5, and I'll be doing it as 10, and then I'll be like making it over here 9.81, and I'll be writing it, it's going to be negative 9.81, the acceleration. Okay, this is going to be my graph for 2 marks. It's going to be as simple as this. For all of you, you need to realize this is how this question is done. If any one of you wants to have the mark scheme or the paper or the book, they can ask me on my WhatsApp, or they can even ask me on the email. I'll give them. Okay, The ball falls through rest, air from rest. Okay, the ball falls through the air from rest. Which of the following shows the graph of displacement against time for the ball? I told you that displacement time graphs, we only use acceleration. There's no decreasing, increasing acceleration. So first graph is not going to be there because it's a rest graph. The displacement is not changing. Second one is a constant velocity graph. That cannot be the case. If you realize C and D, C, the gradient is increasing. The gradient is increasing. The line is getting steeper. That means velocity is increasing. This is the graph because in this you can actually observe that the velocity is increasing and the graph is experiencing acceleration. So it's going to be C. Why not D? Initially the velocity is more, the velocity is decreasing. It's basically deceleration curve. Whenever we are falling, even falling, an object ball is falling, it can maximum do it. It can reach terminal velocity. The graph can be straight after a curve, but it cannot be like this. It cannot decelerate. So this is basically a deceleration graph that cannot be possible. Meanwhile, in the previous lecture last, we actually discussed this as well. What are the graphs are going to look like with air resistance? So the acceleration time graph, the displacement time graph can be a curve upward and downward like this. So this actually represents this particular graph, which we have already discussed in the previous lesson. All right, the car accelerated along a straight road. The graph shows how the acceleration of the car varied with time. So it's okay, the acceleration is decreasing. So it's a decreasing acceleration curve. Very good. And then the after that acceleration is increasing. Acceleration is like the other way. Okay, velocity time graph. Very good. Okay, decreasing acceleration. So acceleration you can clearly observe is decreasing. It's decreasing acceleration. So that means the velocity time graph would be a curved. So for the first part of the journey, this is uniform velocity. That cannot be the case. Why is that? Because acceleration is changing. It cannot be uniform velocity. Definitely velocity is supposed to change. Okay. If the graph would have been a straight line, this shows that it would have been a uniform acceleration curve. And this is basically velocity time graph of a uniform acceleration. See, straight line, uniform acceleration, the acceleration is going to stay the same for this. So therefore, D cannot be the case. I'm just going to cut out the values that I think are not correct. Okay. For C and A, now this is a very confusing point. So initially there was around somewhat around a constant velocity and the velocity's magnitude is decreasing. Well, the velocity decreasing, this should have been deceleration. Getting my point? If the velocity is decreasing, that means this should have been deceleration, and it is basically decreasing acceleration positively. So decreasing acceleration would have a curve like this, and then over here it's basically acceleration is like once it reaches zero, that means at zero the velocity became constant, so it's going to be a straight line over here, and then the acceleration became negative, so you can realize this is a deceleration curve. See, so it's an like over here it's decreasing acceleration, and from this point down it's basically deceleration because the velocity, now the acceleration is going down, it's a negative, so the graph can only be A very technical question, but it's A. I hope you understand my point. This is decreasing acceleration, so decreasing acceleration on a velocity time graph goes like this, and then this negative, it's deceleration, so it goes like this. I'm going to combine those two and get the value. It's going to be A. All right, now this is an extremely amazing question as well. The graph obtained by the student is shown below. Explain the shape of the graph. It's a displacement time graph, and if you actually realize that it starts from rest because it's a straight line. Initially there's a curve, and the curve continues to about, you'll put a scale over here. You'll actually put a scale over here. This is how you're going to be doing it in the exam as well. And the curve continues around somewhere, I'm not sure. Shit, man, I'll be putting a scale. It's so easy putting a scale when it's a real one. All right, so it continues, the curve continues around somewhere over here. Okay? This is where the curve continues. All right. So you can say that it starts from rest. The gradient is negatively increasing. So that means the object is coming back towards its original position with the velocity being increased. So from time 0 to time 0.6 after starting from rest, the graph, like the since the gradient is increasing, you can clearly say that the velocity is increasing and object is coming to the left, like or to the original position in the opposite direction. Therefore, the velocity is negative. At time 0.6, the object is moving with uniform velocity and till 1.8, 1.16. Since 1.16 seconds, the object is moving with constant velocity. So this is going to be three lines. Number one, starts from rest. Velocity is going to increasing till time 0.6 seconds. And you can say object, yeah, what is object is coming towards original position, or I can safely say moving in negative direction. And then at time 0.6 seconds, it starts moving with a uniform velocity, reaching starting position, reaching original position at time t is equals to 1.16 seconds. This is pretty much a lot of questions that we have discussed so far. I'm hoping that you guys are understanding my concepts or the points. We'll be covering a couple of more MCQs and then we'll call it a day. And the remaining questions we'll be doing in the next lecture. So graph can be used to represent the motion of the object. Okay. Now, quantity plotted on y-axis, time against. Okay, so what would be plotted over here? That would give a gradient of acceleration. Okay, velocity time graphs gradient gives us acceleration. It's very simple. It's v. So if it would have been an acceleration time graph. So acceleration time graphs gives velocity, not necessarily. Acceleration times graph area, not the gradient, rather area gives us change in velocity. And there's nothing else that can happen. Displacement time graphs, area does not give us, or gradient does not give us acceleration, it gives us velocity. So it would have been velocity over here. Velocity times graph gives acceleration, acceleration does not give that, and then that's it. Okay. There are two last questions that we will be discussing. Stay with me, pause the video if you want to try it yourself, and then listen to what I'm going to say. Okay. The velocity time graph for the motion of the ball is shown. Which of the following correctly describes the motion of the ball? Again, we have discussed this whole question. The ball is gaining velocity, that means it's going down, rebounding and coming back to its original position. Oh, rebounding, changing velocity's direction. It's basically like rebounding concept. The ball is dropped and rebounds to a lower position, and that's pretty much anything that we can say. The ball drop rebounds to the original position. No, it does not rebound to the original position because this area and this area is not same. If this area would have been same, it would have rebounded on its original position. Now, this is a concept that I think can be discussed one more time. We have discussed this concept initially, and we did a rebounding concept regarding the elastic collision. So if the ball goes down and then comes like half of it, this graph stays the same, but then this graph is like a little bit like this, or like a little bit like this. So it's not like actually the same, like areas are not same, because it is not possible even in the real world. If the ball bounces, it comes to a like less height, it like reduces some height, loses some height because it loses some gravitational potential and kinetic energy. So the graph shape is more like the one we just did in the question. Okay. Last but not the least, which of the following graph of displacement against time could represent the motion of the ball? Okay. Which ball? This ball? All right. Which of the following graph of displacement time could represent the motion of the ball. Okay, this ball. Okay, velocity is increasing. That means the displacement time graph would have to show acceleration, and the gradient would have been increasing very well. And then it rebounds and decelerate. So displacement time graph would have to show deceleration. And yeah, it's like, let's say if displacement cannot be negative now, because object is like throughout, like above this point. So if it, like, let's say if this is the zero position and the object is going down, and it's going to be like this, and then when it bounces it's going to come back again, so it's going to be like towards its mean position, so it would exactly be C rather than A. This is again very important concept. If assuming this is the ball and the ball goes down and the displacement is covered positively, because this is like wrong, because the velocity is uniform in this, and it cannot be the case because velocity is increasing. This is a uniform, like graph of uniform velocity, because displacement time graph gradient gives us velocity. So since the velocity is changing, B cannot be the answer. So far as D cannot be the answer. When it comes to A and C, a lot of student gets confused. When it comes to A, as the ball is going down, I'm saying that displacement is covered in positive in both of the case scenarios. And okay. And when it bounces back, it comes up. That means now it's coming back to its position. Like displacement is covered positively. So this whole region is positive displacement. If it comes over here, the displacement would be like positive. After, in case if this ball would have passed this point and goes up, in that case scenario, it would have been like something other than A, but it's still not A. It would be something like this and then eventually going down. So in this scenario is completely wrong. This only can be C. And that's pretty much a lot of questions that we have done regarding motion of graphs. There's still a very important lecture that we will be discussing in the next class regarding this motion. We have got some amazing questions, and then we'll call it this topic ended. So stay tuned for the next lecture so that we can cover more graph questions. See you in the next lecture. Take care, guys. Since you're enjoying the lectures, just wanted to inform you that there are premium batches going on. That is a direct way to get A's and A stars. It has got some exclusive content that is not generally available neither on the website nor on the YouTube. So you can join the batch to get your grade.